Well, hello again, everybody. It's Zach again. Today I'm going to give another math presentation. This one is on irrational numbers. To start off, we have to go all the way back to the Greek philosopher Hippasus, who lived around the 5th century BC. Hippasus belonged to a group of philosophers known as the Pythagorean mathematicians. Their dictum of all is number suggested that numbers were the building blocks of the universe. And part of this idea was that everything, from cosmology and metaphysics to music and morals, followed eternal rules that could be described as ratios of numbers. Thus, any number could be expressed as such a ratio. 5 as 5 over 1, 0.5 as 1 over 2, even this extended decimal could be rewritten as 1 over 9. We now refer to these as rational numbers, but Hippasus found one number that violated this rule, one that was never meant to actually exist. The problem began with a simple shape, a square that had a side length of 1 unit. According to the Pythagorean theorem, the diagonal must equal the square root of 2. But try as he might, Hippasus could not find such a ratio that equaled this new number, and instead of giving up, he decided to prove that it could not be done. He first went on to assume that the square root of 2 could be expressed as such a ratio. He labeled this ratio P over Q, and when this ratio was in its simplest form, P and Q would not have any common factors. He first got rid of the fraction by multiplying both sides by Q, and then squaring each side, which left him with 2Q squared equals P squared. Multiplying any number by 2 gives an even number, meaning P squared was even. That couldn't be true if P was odd, since the square of any odd number is always odd. So if P squared was even, then P was even as well. He then went on to say that P equals 2a, where a is an integer. Substituting 2a for P and then simplifying gave him Q squared equals 2a squared. Once again, multiplying 2 by any number gives us an even number, so Q squared was even, meaning Q was even as well. And if P and Q are both even, that means that they share a common factor of 2, which contradicts the original assumption. And that is how Hippasus concluded that no such ratio exists. This is what's known as a proof by contradiction, and according to legend, the gods did not like being contradicted. Interestingly, although we can't express irrational numbers as ratios, it is possible to precisely plot some of them on the number line. Take root 2, where we have a right triangle with a leg of 1 and a height of 1. The hypotenuse is square root of 2, which can be extended among the number line. Then, make another right triangle with a leg of square root of 2 and a height of 1. The hypotenuse is square root of 3, which can also be extended among the number line, and so on. The key here is that decimals and fractions are ways of representing numbers. Square root of 2 is just the hypotenuse of a triangle that has legs of 1 unit. Another example, the famous irrational number pi is always equal to what it represents, the ratio of a circle's circumference to its diameter. But approximations such as 22 over 7 or 355 over 113 will never precisely equal pi. We may never truly know what happened to Hippasus, but we do know that his discovery revolutionized mathematics. So whatever the myths may say, never be afraid to explore the impossible.